Mr. Malenga here. I want us today to look at heat under thermophysics, in particular specific heat capacity. So actually, basically, you realize that when different liquids, let's say cooking oil and water, are heated by the same amount of heat, containing equal amount of these liquids, when they are heated, you realize that one gets heated faster than the other. What's the reason? It is because they have different abilities to hold heat. They've got different abilities to absorb the heat. So today I want us to look at what is called specific heat capacity. So how do you actually explain specific heat capacity? So like I said, when two liquids are heated, we expect them to undergo a temperature rise. Okay, we expect them to undergo a temperature rise. But you realize that if it's the same water, let's say 2 kilograms of water here, and in here we have 7 kilograms of water. When we actually apply the same amount of heat, we'll realize that this water will be heated faster than this one in here. Why? Because we have more molecules of water in the 2 kilogram of water than they are in a 7 kilogram of water. But now, when we say, let us have the same amount of liquids, then just change types of liquid. So let's say in here, we get to have 2 kilograms of water, 2 kilograms of water, and in here we get to have 2 kilograms of cooking oil. If they are both receiving the same amount of heat. Now here, because the masses are the same, but when they are heated, we actually expect them to actually undergo a temperature rise. So from the beginning of it, at the beginning of the experiment, the amount of temperature that we can record, and at the end of the experiment, the temperature that we record, we can actually look at the difference that gives us delta T. But now, if we consider the differences in the makeup of this liquid, it brings about this value here we call specific heat capacity. So actually, how much of water is contributing to the temperature rise? So this heat is given a symbol Q. So actually, the amount of heat that heats up a liquid or that causes a temperature rise depends on these two things. One, we're actually talking about the mass of the liquid, which brings about the temperature difference as well as the specific heat capacity. So different liquids have got different capacities. That what causes them to get heated at different times. So now, how do you actually define specific heat capacity? So in simpler terms, specific heat capacity, allow me to write it up here. Specific heat capacity is actually the amount of heat supplied to a liquid that can cause temperature rise by 1 degree. Let me add a little bit of verse to the definition. So we're saying specific heat capacity, let me write it here. Specific heat capacity is the amount of heat needed to raise the temperature, to raise the temperature of a 1 kilogram mass liquid by 1 degree Celsius. So that is what is called specific heat capacity. So specific heat capacity, we're saying that the amount of heat needed to raise the temperature of a kilogram mass liquid by a single degree Celsius. That's what we call specific heat capacity. So different liquids, if they have different specific heat capacities, if they need different amounts of heat to cause the temperature rise by a single degrees for a kilogram mass of that liquid, we expect them to be heated differently. So quickly, let me just take you through the notes that we have here. So we're saying that just a quick one. It says that if a kilogram mass of water and a kilogram mass of paraffin, they are heated at the same time by the same heater, we'll find that the temperature rise of paraffin is 2 times faster. In short, paraffin gets heated faster than water. What's the reason? They have different specific heat capacities. Depending on the arrangement of bonds, depending on the bond order, depending on the bond length, depending on the types of atoms present, that's what brings about differences in the specific heat capacity. So we're saying that the amount, it seems that different substances, in short liquids, differ the amount of heat that can cause the temperature rise of a single kilogram mass by 1 degree Celsius. So the thirst for a substance for heat is measured in terms of specific heat capacity. So we're saying that different liquids have got the thirst for heat. Different liquids have got different thirsts for heat. And that's the reason as well when you look at metals, metals are so rigid, atoms are so close to each other, you realize that these guys, they do not have much thirst for water. They don't have much thirst for heat. As a result, even when they are heated, it needs to take a lot of heat for them to actually undergo a temperature rise. So that's basically what we actually look at today. So the specific heat capacity is also defined down here, where it says the specific heat capacity of a substance is the heat required to produce, that is to cause a temperature rise, to cause a degrees Celsius rise in a kilogram of a substance. So actually, we can measure specific heat capacities of different liquids. Could be water, could be oil, could be paraffin, could be kerosene, that's kerosene, could be bitumen, all different liquids that we can have. We can actually measure the specific heat capacities. Now, how do you do that? We're actually going to look at that below here. Now, if you can allow me to actually maintain the right up here and just do maybe a little bit of scrolling down, can I make a pretty good presentation? So here we say that heat, like other forms of energy, is measured in joules. So here now we're trying to find the beta or the best SI units in which these physical quantities are actually measured. So heat, down there, I'm going to give you the symbols. I'm also going to give you the units. Okay? 3 things. We're talking about the amount of heat. So heat should have the symbol, should have the units. Then the temperature rise. We're going to have the symbol for temperature. We're also going to have the units for temperature. And therefore, also talking about the mass, we need to look at the units as well as the symbol. Okay. So maybe I can do that right now. So heat, I don't know where I can write it. Maybe if I could slide this thing here, then maybe I use different color, maybe like white. So we can actually start with heat. So heat actually has a symbol capital Q and the units. The units for heat is a form of energy which is measured in joules. That's number one. Number two, we're actually going to look at temperature. Temperature whose symbol we know it's T, but we're talking about temperature change. Temperature change. So the change in temperature is actually denoted by a Greek letter which is called theta. And sometimes this theta is actually represented, is used to represent angles. So this temperature, we're talking about a temperature change, so we can actually say delta theta. So because we're talking about the change in temperature from one value to the other, so the delta is actually talking about the change in theta. So this is the temperature. And in what units, in which units is this temperature measured? Today, we understand very well from the basics of chemistry that basics of physics that temperature is measured in Kelvin as SI units, but for today, we're actually going to stick to degrees Celsius. Okay, the other thing that we actually have is the mass. And mass, the symbol is M, we understand that very well, but the units are actually kilogram. So you see, mass can be measured in pounds, mass can be measured in kilogram, mass can be measured in grams, in milligram, and all those things. But the units that we're going to deal with today are actually kilogram. Okay, so we should be able to actually find these things. But the last one is the specific heat capacity. So specific heat capacity, the symbol that we use is capital C. So I'm going to use the abbreviation specific heat capacity. Specific heat capacity, HC. So the symbol that we use is actually capital C, and the units, I'll show you where these units are coming from. So the units are kilogram per, I'm leaving space for degrees Celsius. I can't quite do the writing easier. Degrees Celsius. Okay, let's say the specific heat capacity. Okay, specific heat capacity is actually measured in joules per, yeah, in joules per kilogram, and then per, the same per dividing by degrees Celsius. So this is a formula, or these are the units in which the specific heat capacity is actually measured. In joules, this is heat coming from heat, is coming from heat. This is actually coming from mass, and this is actually coming from temperature. So specific heat capacity, the units are actually the combination of these three things. So right from here, we should have an idea. You know, at times we can get the formula from the definition, can also get the formula right from the units. So if we are to find the specific heat capacity, the only way in which these units can actually be obtained is when we have heat on top, okay? When we have heat on top, theta, divided by kilogram, and then you see the kilogram and degrees Celsius are not divided. These two actually are being multiplied. So we can even say delta theta. So actually, this is Q. We can actually get the formula for specific heat capacity right from the units, because we're told that specific heat capacity is measured in joules per kilogram degree Celsius. So because the joules are on top, we know that the temperature is on top, heat, and then we actually have on top here, we're talking about the amount of heat energy in joules, then divided by the product of mass, as well as the change in temperature. So actually, when you're dealing with this experiment, you need to take note of the initial temperature at the beginning of the experiment. You take down of the initial temperature at the beginning of the experiment. You also need to take down the final temperature reading at the end of the experiment, so that you're able to subtract the two in trying to get the delta theta, the change in temperature. So let's look at this write-up that's here. So we're saying that if a substance, we don't know a substance, it's just presumption, that if a substance has the specific heat capacity of 1,000 joules per kilogram degree Celsius, it means that is the amount of heat that that substance needs actually to have its temperature rise by a single degrees for 1,000 grams or for a kilogram mass of that substance. It means we need 1,000 joules of energy to have a kilogram mass of the substance, its temperature rise by single degrees. Meaning if we actually increase the heat twice, we expect the temperature to increase by twice, or we actually can heat another set of a kilogram by a single degree. In short, we can heat 2 kilogram mass of the same substance by a single degree, or we can actually increase the temperature of a single kilogram by 2. These are direct proportional computations. So this is basically what is also talked about here and there. Now, what does it mean? If we have 6,000 joules, it means we can actually increase the temperature of a 2 kilogram by 3 degrees. Or in other words, can actually increase the temperature of a 6 kilogram mass by a single degree. Or we can actually increase the temperature of a single kilogram mass substance by 6 degrees. It's either way. I wish you understand what I'm talking about. So how do you do that? We are actually multiplying these three things. You increase the specific heat capacity, you expect the temperature to increase if you keep the mass constant, or you expect the mass to increase if you keep the temperature constant, or you expect both to increase if you do a proper, good job of division. So that is basically what this illustration is all about. Now down here we have some examples. So some examples here are actually saying, if the temperature of a substance fell by, so actually the temperature of a 2 kilogram mass is reduced by that value. It means, now remember, there are two important aspects that we're going to look at: exothermic and endothermic. So for specific heat capacity, we're talking about the energy needed. So actually this energy should be absorbed by a liquid, endothermic. Meaning when the temperature of that liquid drops, meaning that temperature which has dropped, the amount of energy lost has been gained by the environment, and that's exothermic. So actually here we are talking about an open system. Talking about an open system where both matter and energy are being exchanged. Yeah, should I say closed system? Only energy is being exchanged, but the matter remains constant. Yeah, we're talking about a closed system. Now, let's look at the formula, the one that I'd given here, where I said C, specific heat capacity, is equal to the amount of heat energy divided by kilogram multiplied by change temperature. But if we are to make Q subject of the formula, we are actually going to multiply these three. So Q, we can have Q here being equal to the multiplication here. So if the best is we start with the mass in kilogram. Yeah, here's the mass. Mass in kilogram, multiply by the change in temperature, multiply by the specific heat capacity. So you can actually switch them because you see multiplication doesn't really matter. But the thing is when you multiply them, definitely get the answer. So even if you had switched them, you'll still get the same answer. Yeah, so that's what we are talking about. So this is what we have here. What it says that the amount of heat received is the same amount of heat. If the substance loses heat, that heat will be received by the environment. And when the environment loses heat, that heat will actually be gained by the system, which is a substance. So let's look at the example that we have here. The example down here says that for example, if the temperature of a 5 kilogram mass, so the temperature here of the mass is 5 kilogram, the temperature of a 5 kilogram mass of the material of the specific heat capacity of 400 joules per kilogram degree centigrade rises the temperature from 15 to 25. Calculate the amount of heat received. So how much of heat energy caused the 5 kilogram mass of that material to undergo the temperature increase, the temperature rise from 15 to 25. So maybe the best that I can actually do is to do that. I'm gonna crop a little bit this part so that we can find, first of all, we find the change in temperature. So we first of all find the change in temperature. Yeah, just for illustration sake. So the change in temperature, we are actually saying it's from 25 to 15. This actually gives us, a 10 degrees centigrade. That's a change in temperature. The specific heat capacity they have already given us to be 400 joules per kilogram degree centigrade. And the mass is already given here. We're given that the mass is actually 5 kilogram. So we are here to find the value of Q. So Q is equal to mass multiplied by the change in temperature, delta theta, multiplied by the specific heat capacity. So we're gonna multiply, and you will find that at the end of this, the units should cancel out. So the mass is 5 kilogram multiplied by the change in temperature is actually 10 degrees centigrade multiplied by the specific heat capacity is 400. And that's the beauty of such questions, is because they are able to cancel out. So joules per kilogram degrees centigrade. So right from here, we can actually see what happens, where we have the kilogram and the kilogram, because the kilogram here is the numerator, the kilogram here is the denominator, they cancel out. The degree centigrade here is the numerator, the degree centigrade here is the denominator, they've cancelled out, and the only persisting units that we have so far are the joules. And therefore, the amount of energy that is responsible to have a 5 kilogram mass of the substance to have its temperature rise from 15 to 25 is, so we're gonna do 4 times 5. This actually gives us a 20. And then we have this 0, we add it here. We have that 0, we add it there. We also have that 0, we add it there. So this is a temperature. This is the amount of heat that was responsible to have a 5 kilogram mass of that substance to have its temperature rise by 15 degrees centigrade. Okay, that is what we have. Now let's look at the next thing just within a blink of an eye, which is called the thermal capacity. So what is thermal capacity? Thermal capacity and specific heat capacity, they are almost the same, but except that for thermal capacity, there are some few aspects that are not actually considered. So if you understand the specific heat capacity, we are actually talking about these very things. So let's see what happens. So the question here says, the statement here says, thermal capacity of a body is just the quantity of heat needed to raise the temperature of the entire body by a single degree centigrade. So the only difference that we have here is that mass is not being considered. The mass is actually not being considered. So meaning, to find the specific heat capacity, we multiplied specific heat capacity multiplied by the mass, also multiplied by the temperature change. But in here, we are not considering the mass. So it's the same formula, but we just omit the mass. This is what we have. So let's see what we have down here. So it's just like a single question that we have, which is actually saying that thermal capacity is measured in joules per cubic centimeter. The mass is not there because specific capacity joules per kilogram degrees centigrade. So that's the difference. So the question here says for a copper block, okay, the entire thing, not part by parts, the entire thing was measured. The entire thing was measured. And its mass was actually 100 grams, 0.1 kilogram. Whose specific heat capacity is that? That specific heat capacity. Now, calculate the thermal capacity. So thermal capacity, we actually gonna multiply, or the mass is actually at play, but we are not taking account the temperature. That's the reason as to why in our computation, you'll find that when you do the multiplication here, because the mass is measured in kilogram, the mass is measured in kilogram, and then the specific heat capacity is joules per kilogram degrees centigrade. So only these two items are cancelling, and the units remaining are joules per temperature. Also saying the amount of heat energy needed to raise the entire body of a substance by 8 degrees centigrade. Okay, so that is how this question was actually solved. So we have a question saying for a copper block of mass 0.1 actually has the specific heat capacity of 390 joules per kilogram degree centigrade. Calculate the thermal capacity. So thermal capacity, we are saying it's mass times the specific heat capacity. So like I explained, this thing cancels and that thing cancels. Then you multiply the mass and specific heat capacity, and the units are the joules per degrees centigrade. And actually, this is how this entire question was solved. Unless there are questions, we can raise our case right here. Okay, now maybe let me just run through. How do you measure now the specific heat capacity? We don't just use any object. The best that we can actually use is a calorimeter. Why are we using a calorimeter? It's because the calorimeter has the ability to retain enough heat within the system. We do not want to have a situation whereby this heat is absorbed by the liquid, and yet, okay, let me say this is the system where we have the water being heated, and now if this is a very good conductor of heat, we expect heat to be lost to the environment through conduction, radiation, and convection. That's why we need a calorimeter, because a calorimeter is a very bad conductor of heat, which does not allow the heat loss. So it's gonna be the best thing to use. So what do? We cannot measure how much of heat is coming from charcoal. It's quite unfortunate. So all we need to use is a power supply with a known power rating. So the power supply, here we need the power supply, power supply with a known rating, If we say 40 watts, it means this power source has the capacity to convert 40 kilojoules of energy into heat energy per second. So we actually know how much of energy is being produced per second. So that when we say that this thing has been turned on for a minute, we're going to multiply that each second 400 joules was used, each second 400 joules was used, and how many seconds are in a minute? 60. So we can actually multiply 60 by 4, which can give us 24,000 joules as the amount of heat produced and not produced, released by the heater and absorbed by the liquid for as long as it is an isolated system where exchange of matter is not, exchange of heat is not involved. Okay, then the other thing that we need to use is actually we need a thermometer, because the thermometer is going to help us to detect the temperature change. So the rise in temperature can only be measured by a thermometer. And then the other thing that we actually need is the beam balance, because the beam balance is going to help us measure the mass. So here's a setup. Let me just run it through. So we have the heating element here with a known power rating. Like the way they explained here, maybe they say 40 joules. We're trying to measure specific heat capacity of water. So you connect this thing here in there, and then you dip in the thermometer and record the initial temperature, T1. Most of the times when thermodynamics conditions are all met, we take it that the room temperature is 25 degrees centigrade. So let's say this is T1. We dip in the thermometer, we dip this thing in and turn it on at the very time you start the stopwatch. Okay, that happened, the heating continues, the heating. But now remember, this heat can be lost from this water by the method or by the process of convection. So it's important that we have a closed system. That's why we are closing it here. So the best to use is the calorimeter. This can be a calorimeter. Okay, so you close it and then you actually allow this experiment to go through. Now, we can't just let it go like that. We can say, let us take time to be maybe just say 2 minutes. So that when you say how many seconds are in there, 60. So multiply by 2, we know that it's 120 seconds. 120 seconds. And then we can know how much of electric energy has been converted to heat energy according to fundamental laws of energy conversion. So we'll say that the amount of energy you can multiply. Remember from the physics electricity point of view, where we say that potential energy is the amount of energy converted. So PD, okay, let me do this. Yeah, let me take you back to a bit of electricity. So we say PD, potential energy, is the amount of energy, which volts. PD is the amount of energy. PD is the amount of energy converted to each coulomb of charge per time. So that's why we are saying you multiply this and that to get the power. Now, here what we are actually doing is that we need to know how much of energy was used. So if each second we use 40, each second we use 40, each second we use 40, then we can multiply by that to know how much of energy was raised. So after you do this, you know how much of energy is there. You also know the mass. You also know the change in temperature. Then you can use the appropriate formula to find the specific heat capacity, where we actually divide the amount of energy divided by the mass multiplied by change in temperature. That is how you can find a specific heat capacity.